Acidic conditions can also be used to open epoxides with a weak nucleophile, such as HCl, HBr, water, or an alcohol. This ends up getting more complicated when it comes to regioselectivity. But in this reaction, the first step is you protonate the oxygen with the acid. And now we have a very, very electrophilic epoxide. So now the X minus is going to come in and attack one of the two carbons, opening up the ring, and then we get this resulting product. So we can use water or alcohol as well with acidic conditions. So if we use alcohol, the OR is the nucleophile. If we use water, OH ends up adding to the epoxide. Antifreeze, also known as ethylene glycol, is made industrially using this method. So this shows the acid catalyzed mechanism for the addition of water. So first you protonate the oxygen, and now we have this really, really electrophilic epoxide. And then the nucleophile is going to attack one of the two carbons of the epoxide, opening up the ring. And then we get to this intermediate where water attacked, but this is a positively charged oxygen, so we're going to do one more proton transfer because we always want to end up with neutral products. So we're going to grab that hydrogen, those two electrons fold in and form a second lone pair on the oxygen, and then we've reformed our acid in the process, which is why this is just acid catalyzed, because we're regenerating the acid as we go along. Now where it gets complicated with acidic conditions for epoxide opening is that if you have a primary versus a secondary, the nucleophilic attack still occurs with the less substituted carbon. So that's just like what we saw with strong nucleophiles. But if you have a tertiary carbon present, the nucleophile switches and attacks there. So here the nucleophile attacks at the tertiary carbon. Now the reason for this is that the epoxide is positively charged under acidic conditions, and when you have a tertiary carbon, it will be able to stabilize the partial positive charge better than a primary or a secondary. So this bond ends up being weaker, and you have more of a partial positive on that carbon. When you don't have a tertiary carbon, that effect is not as strong, and then the steric effect dominates, where the nucleophile is just going to attack at the most accessible carbon with less atoms in the way. So here we have competing steric versus electronic effects. So in one case, the electronic effect wins when you have a tertiary carbon. In the other case, when you don't have a tertiary carbon to choose from, the steric effect wins out. But regardless of which carbon is attacked, you still get inversion of configuration. Now let's try epoxide opening in acidic media. So notice all of these have an acid, which is going to change, in some cases, which carbon the nucleophile is added to. So let's look at part A here. We've got the simplest epoxide possible with HCl. So first, the oxygen of the epoxide gets protonated when we're in acid, and then the Cl- will come in and open up the epoxide ring to give the product shown. So for all of these, B through F, I want you to try to figure out the product and then take a picture of what you drew as the product, paste it into the chat, along with an explanation of how you got that product. Now remember that when we're in acid, the regiochemistry can change. When we have a strong nucleophile, and the last set of problems, the nucleophile always adds to the less hindered carbon. But with acid, the rules are a little bit different. With acid, if we have a competition between a secondary and a tertiary carbon, it will add to the tertiary carbon. However, if we have a competition between a primary and a secondary, it will add to the primary. So here, look at these problems, choose one, try to figure out the product, then take a picture of your product and paste it into the chat. Now we're going to finish up with thiols and sulfides. So a thiol is just simply the sulfur analog of an alcohol. So instead of having an OH group, you're going to have an SH group. Thiols are also sometimes called mercaptans. And when you name this, it's analogous to naming an alcohol, but instead of ending the name in OL, you're going to end the name in thiol. The mercapto prefix is also used when you want to name that group as a substituent. So this would become 3-mercapto 3-methyl 1-butanol. And this is an example of a thiol that's used to treat mercury poisoning. Thiols are well known for their unpleasant odor. Indeed, skunks use thiols as a defense mechanism. And methane thiol is added to natural gas so that gas leaks can be detected, because methane doesn't have an odor, so you have to add something stinky to it to alert people that there's a gas leak. The hydrosulfide ion, HS-, is a strong nucleophile and a weak base, and that's why it promotes SN2 rather than E2 reactions. Primary and secondary thiols can be synthesized from an SN2 reaction of sodium hydrogen sulfide. Primary and secondary thiols can be synthesized via an SN2 reaction using sodium hydrosulfide with an alkyl halide. So here all that's happening is you have this nucleophile, and it's simply attacking the carbon with the leaving group and kicking off the leaving group. Thiols can be oxidized to disulfides in the presence of bromine under basic conditions. So these are basic conditions because it has sodium hydroxide, which is a strong base. And the way this works is that first you use that strong base to deprotonate your thiol, and then it's going to attack the bromine molecule, adding a bromine. And then the second molecule of the thiolate attacks the sulfur, kicking off the bromide. So it's two types of nucleophilic attacks in the same reaction. A disulfide can be reduced back to the corresponding thiol using zinc metal and HCl. The bond association energy of a sulfur-sulfur bond is not that great, so the bond is easily made and broken. And this is important because the shape of proteins relies on the sulfur-sulfur bond being easily broken and easily made. Sulfur analogs of ethers are called sulfides or thioethers. And this can be named similarly to how ethers are named. So this could be called diethyl sulfide. It can also be named as a substituent. So this could be called the methyl thio group. When added to the whole name, you would get 1,1-dichloro-4-methylthiocyclohexane. Sulfides are generally prepared by nucleophilic attack of a thiolate on an alkyl halide. So a thiolate is just this generic structure here, where you have a negatively charged sulfur bonded to some R group. So here the nucleophile simply attacks the alkyl halide, kicking off the leaving group in standard SN2 fashion. So for this one, what is the correct name for the following? I had originally written IUPAC, but I'm actually looking for the common name. For this reaction, what is the product? And as a clue, this is an example of the Williamson ether synthesis. And then finally, what would be the correct order of reagents needed for the following transformation? So choose from these answer choices here. That's it. Thanks for watching this video.